If the universe was once smaller than an atom, what allowed it to become a place of galaxies, stars, and planets in time? And in that first instant, who decided the fate of everything? An invisible pull, or a deviation so small it was almost negligible. You can imagine that if gravity had been just a fraction weaker, everything would have drifted apart forever, cold and empty. But if it had been a fraction stronger, the universe would have collapsed into dense, dark regions before it could ever expand into any structure. So, how did the universe land exactly in that perfect middle ground? And if it had been off by just one notch, would there still be room for light, for matter, and for our story? At the earliest moment science can trace back, space had not yet expanded as it has today. Everything existed in a state so compressed that the very concept of distance barely existed. Modern cosmological models suggest that the entire mass and energy of the roughly 400 billion galaxies observable today was once packed into a region of space smaller than the size of an atom. If you took 1 centimeter and divided it into a billion parts, then divided one of those parts into another million pieces, the size of the observable universe at that time would fit within that range. It was a space of almost zero volume, yet it contained everything that would become stars, planets, gas, dust, and the massive structures of the future. In that state, familiar matter, like atoms or molecules, did not yet exist. One can imagine it as an extremely hot and dense point of energy where everything was blended together. No boundaries, no shapes, no empty space. The temperature and density was so immense that every everyday concept became useless. The contrast between this tiny starting point and the current universe, with its vast carpets of galaxies, is a distance that is almost absolute. From that foundation of extreme compression, the universe began to expand. As space opened up, the temperature gradually dropped. In the early stages, the universe remained formless. No stars, no galaxies, just a thick sea of energy. It was during this expansion that the familiar laws of physics began to stabilize, and the fundamental forces started to split away from their common original source. In those first moments, it is imagined that all fundamental forces were once one. As the universe cooled, they separated into individual types with specific roles. Among them, gravity was the most dominant force on a large scale. This is the force that makes everything with mass attract each other. Later on, it was gravity that decided which clouds of matter would gather to form stars, star clusters, galaxies, and the entire cosmic web. At this starting point, gravity acted like a silent rule, determining whether the universe would thin out forever or manage to gather into concentrations of matter. Gravity is not just a simple pull. On a cosmic scale, it decides the entire fate of space and time. If this attraction were a bit weaker, the way the universe expands would be different. If it were a bit stronger, dense regions would have progressed in the exact opposite direction. Even a tiny change in its intensity would have rewritten the blueprint for cosmic structure from the very beginning. To see the extent of that sensitivity, cosmologists have used supercomputers to test it. Carlos Frenk and his colleagues built numerical simulations in which a universe is created using imaginary particles with mass, position, and velocity, then allowed them to follow known physical equations. By changing the parameters bit by bit, they could observe how a universe would evolve under different conditions. When simulating a universe with less gravity than in reality, the result was almost entirely empty space. In the simulation, the initial points of matter drifted apart very quickly as space expanded. Gravity was too weak to pull them together to form large gas clouds. No galaxies appeared, no stars, no galaxy clusters. It was simply a thinning universe where the density of matter continuously dropped, and no significant structures formed. That image suggests a universe that exists but where nothing happens on a large scale. There are no concentrations of energy to provide light, no planetary surfaces, and no complex processes. Everything seems spread out and faint. Such a universe, structurally speaking, is a failed experiment. Conversely, when programming a universe with gravity stronger than the current level, the simulation also produced unstable results. Matter in those models was quickly pulled together by the force of attraction. Instead of forming steady gas clouds that evolved gradually, dense regions collapsed violently, creating many massive black holes. The expansion of space was not enough to balance this inward pull. In that context, the simulated universe did not have time to develop delicate structures. The time needed to form stars, planets, or spiral galaxies was cut short or non-existent. Matter was locked in extremely dense, dark regions. Once again, the overall structure became impoverished in a different way, too heavy, too collapsed, lacking the space for more complex processes. The two opposing sets of simulations lead to one conclusion. If gravity were a bit weaker, the universe would disperse too quickly and remain empty. If it were a bit stronger, the universe would collapse into dark, dense regions. Between these two extremes, there exists only a very narrow window where the attraction is strong enough to gather matter, but light enough to allow space to continue expanding. Scientists call this a just right scenario. The Big Bang seems to have launched the universe with an amount of gravity falling exactly within this range. Not too weak to let everything dissolve, and not too strong to let everything collapse, with only a slight adjustment from its current value. Simulations show that cosmic history would be entirely different, and the familiar structures of today would be unlikely to appear. One can imagine this as a mysterious dial, where the position that allows the universe to have galaxies, stars, and planets is just a very thin line among countless possibilities of failure. When the dial is set correctly, gravity is strong enough to pull gas clouds together, creating dense regions, while still allowing space to expand to prevent the universe from pulling itself back into a collapse. The moment of origin, therefore, was not just a simple explosion, but the starting point of a process determined by very specific numbers. From a region smaller than an atom, the universe began its journey of expansion with a just right pull to create the skeleton for all future structures. Gravity, from that moment on, silently shaped the contours of space, deciding which places would solidify and which would thin out. From this fragile foundation of balance, the next part of the story is how the early universe expanded, cooled, and transitioned from a formless sea of energy to the first recognizable structures. In that context, gravity continued to play a central role, leading the formation of dense regions that paved the way for future cosmic explosions. Immediately after the starting moment, the universe did not progress at a leisurely pace. It entered an extreme phase where all familiar concepts of speed, size, and time lost their usual meaning. In a span of time so short it is hard to express in words. Less than a trillionth of a trillionth of a trillionth of a second after the Big Bang, space began to expand. This was not a slow expansion, but a violent swelling. The size of the universe increased by a massive factor, more than 1,000,000 trillion times. These numbers are not meant to be memorized. They exist only to show that such a speed lies entirely outside human experience. If one had to visualize it, think of a shockwave of energy spreading in all directions at once. There was no center, no clear edge. Every point in space was moving away from every other point. Space did not just contain energy, it was being stretched, like a fabric pulled tight in an instant before any stable structure could form. This phase is called cosmic inflation. Its role was not to create stars or planets, but to explain why the universe today is so vast. Without this super-fast expansion, the universe might have remained clumped, dense, and very different from what we observe. Inflation is the bridge between the microscopic world of quantum fluctuations and the macroscopic scale of space today. When speaking of the speed of this expansion, a question almost immediately arises. Nothing can travel faster than light. This is one of the fundamental limits of modern physics. Yet, during the inflation phase, space expanded at a speed far exceeding light. This sounds like a direct violation of familiar laws. The loophole here lies in the interpretation. The speed of light limit applies to matter and information moving through space. It does not apply to space itself. Empty space, physically speaking, is not nothing. It is an entity that can expand, contract, and change its structure. When space itself expands, points within it can move apart faster than light without carrying information in the conventional way. This interpretation helps resolve the conflict between the theory of relativity and the early Big Bang picture. Even so, inflation is an idea that makes many physicists pause for a long time. It is not intuitive. It requires accepting that familiar rules only work well under certain conditions. And the early universe was not one of them. To better visualize the scale of expansion, size comparisons are often used. Before inflation, the universe may have been smaller than an atom. After inflation, in just an incredibly brief moment, it reached a size roughly equivalent to a baseball. This change did not happen over years or seconds, but in a flash so short that conventional clocks cannot measure it. Another more familiar comparison is to imagine a golf ball. If this ball expanded at a similar rate, in that same amount of time, it would swell to the size of the Earth, not twice as big or 100 times bigger, but so large the starting point would no longer be recognizable. These visualizations are not perfect, but they help bridge the gap between abstract numbers and everyday experience. In this context, even the concept of time needs to be redefined. Seconds, minutes, or hours are units built on the steady motion of stable physical systems. But in the early universe, no such stable system existed. Everything changed too quickly. Therefore, physics uses a different unit called Planck time. Planck time is the smallest unit of time that current theories can meaningfully describe. It is so short that in one single second, there are more units of Planck time than the total number of seconds that have passed since the Big Bang, about 14 billion years. This number is not meant for daily calculations. It indicates that in the beginning, events unfolded at a completely different rhythm. If a familiar second was stretched out like a road, Planck time would be just a grain of dust on that road. And in those first moments, the universe changed through every such grain of dust. There was not enough time to form structures, only violent, successive fluctuations. Parallel to the expansion were energy levels and temperatures that are almost unimaginable. The temperature at that time reached trillions of degrees. At this level, atoms could not exist. Even the particles that make up atoms could hardly maintain a stable state. Every familiar bond was broken almost instantly. If placed next to this moment, the cores of the hottest stars today would be considered peaceful. There, nuclear reactions occur steadily. But in the early universe, energy was like a storm with no center and no preferred direction. It spread throughout the expanding space, constantly transforming. In such an environment, there was no concept of matter in the usual sense. No atoms, no molecules, no durable structures. Only energy in an extremely high state and brief fluctuations. This was a stage where the universe was not yet ready for the existence of anything familiar. However, it was this very violence that laid the groundwork for the next steps. As the universe continued to expand, energy gradually dispersed. The temperature began to drop. The harsh conditions slowly gave way to more stable states. Only then did fundamental particles have the chance to exist for longer than a fleeting moment. The inflation phase and Planck time are not easy chapters to visualize. They exist at the edge of current understanding, but they explain why the universe today has the size, structure, and uniformity we observe. From a state of extreme smallness and chaos, space expanded enough for every subsequent process to have room to take place. As the universe continued to expand, a crucial change began to take place. The temperature no longer remained at its previous extremes. Energy still dominated, but it was no longer entirely free. In this context, a familiar principle of physics began to play its role on a universal scale. The equation E equals mc squared, one of the most famous ideas in physics, proposed by Einstein, is often mentioned in the context of nuclear weapons. There, a tiny amount of matter is broken down to release enormous energy. But in the early universe, the process happened in reverse. It wasn't matter turning into energy, but energy transforming itself into matter. The universe at this point did not need to create matter out of nothing. The only thing required was energy at a sufficiently high level. As space expanded and the temperature dropped below a certain threshold, raw energy began to crystallize into particles. These particles did not appear due to a deliberate design, but as a natural result of changing physical conditions. All matter existing today, from stars to the human body, can be traced back to this stage, not in the form of atoms or molecules, but as very basic subatomic particles. This was the first transition, where the universe moved from a state of pure energy to a state containing matter, albeit in a very primitive form. However, matter at this stage was unlike anything familiar. There were no atoms, no nuclei. There were only fundamental particles that appeared for brief moments, then vanished almost immediately. Energy and matter constantly swapped places, following Einstein's equation exactly, as if there were no clear boundary between the two concepts. One can imagine the universe at this time as an extremely hot and dense soup. In that soup, everything was in a state of constant motion. Particles were created from energy, existed for an instant, then collided and turned back into energy. There was no fixed shape, no stable structure. Everything was temporary. The difference between the early universe and the universe today lies not only in size, but also in its physical nature. The familiar laws of stable matter could not yet be applied. The world at this time was an environment too violent for any long-lasting structure to survive. As the number of subatomic particles began to increase, a new form of chaos emerged. These particles moved at very high speeds because the temperature was still extremely high. They constantly collided, changed direction, and interacted with one another in a space that continued to expand. The image often used to describe this state is a large train station during rush hour. Thousands of people move in different directions at the same time. There is no clear order. Every individual is swept up in the general flow of movement. In the early universe, subatomic particles were just like that. They rushed, dodged, collided, and then separated again. In a station, the chaos comes from high density and a frantic pace of movement. In the early universe, the cause was temperature. High temperature meant high kinetic energy. The hotter the particles, the faster and more unpredictably they moved. This state was accompanied by a very high level of disorder, also known as high entropy. In such an environment, forming a stable structure was nearly impossible. Any combination of particles was quickly broken apart by subsequent collisions. Matter existed, but only as fleeting specks in a continuous flow of movement. Nevertheless, the universe did not stop at this state. As space continued to expand, the energy density dropped. The temperature decreased accordingly. This change happened much slower than during the inflation phase, but it was enough to create an important difference. As the temperature dropped, particles began to slow down, They no longer carried so much kinetic energy as to immediately break every newly formed bond. Collisions still occurred, but they were no longer absolutely destructive. Some particles could exist longer before turning back into energy. The image of the station changed at this point as well. Rush hour gradually ended. The flow of people thinned out. The pace of movement slowed down. Space began to have gaps. In the universe, the same thing happened. Particles were no longer forced to constantly change states. They had time to stay in the form of matter. This process marked a turning point. When the universe was cool enough, energy no longer easily converted back from matter, the equation E equals mc squared still held true. But the conditions for the reverse process to occur became rarer. Matter began to dominate over pure energy. This was a prerequisite for more stable structures to form later. Not yet atoms, and certainly not yet stars or planets. But it was the first time the universe allowed matter to exist long enough to participate in subsequent processes. This stability did not appear all at once. It happened step by step, following the rhythm of the expansion of space. Each time the universe expanded a bit more, the temperature dropped another small notch. And with each drop, the chance for matter to survive increased. This period can be seen as a time of experimentation. Many types of particles appeared. Not all of them lasted long. Some quickly vanished. Others became the foundation for future structures. The universe did not select by will. It only followed the changing physical conditions. Looking back from the present, this process seems like a clear step toward the formation of the familiar world. But at that time, there was no sign of what would last. Everything was still fragile and temporary, even if it was less violent than before. The transition from energy to matter, from chaos to the first seeds of stability, was a long and uneven process. It had no clear ending moment. Instead, it gradually paved the way for a new phase, where particles began to engage in more complex bonds. As the universe continued to cool, the conflicts between particles were no longer just random collisions. They began to follow new, more sophisticated laws. This is the point where the story of matter turned to another chapter, where existence was no longer just fleeting, but began to have the potential to endure. Immediately after energy began to crystallize into particles, a new problem emerged within the young universe. Silent but serious. Matter did not appear alone. Alongside it was a perfect opponent, antimatter. The two sides were so similar they were easily confused. But the moment they touched, both immediately vanished in a flash of energy. Antimatter can be understood as the mirror image of ordinary matter. If a particle carries a positive charge, its corresponding antiparticle will carry a negative charge, and vice versa. The mass, the basic behavior, everything is almost identical. The only real difference lies in the sign of the charge and some quantum properties that are very hard to visualize in everyday life. The most important feature is not appearance or name, but how these two types interact. When a particle of matter and a particle of antimatter meet, they don't bounce off and continue to exist like two colliding marbles. They annihilate each other. The entire mass is converted into energy, following the equation E equals mc squared. The result is a burst of intense radiation, while the two particles themselves disappear. To visualize this easily, imagine a person and a perfect mirror version of that person made of antimatter, two identical figures, standing face to face. If their hands touch, no handshake occurs. Both immediately erupt in a small-scale nuclear explosion. That is the nature of absolute destruction when matter and antimatter meet. In the context of the early universe, the presence of antimatter was not a minor detail. It was a direct threat to the survival of everything that followed. If the two sides were perfectly balanced, every particle that just appeared would be immediately erased from the picture. there would be no chance for structure, no time for any stable thing to form. According to current models, immediately after the universe was cool enough for matter and antimatter to be created, their numbers were nearly equal. Every time a particle appeared, a corresponding antiparticle came with it. It was as if both were born only to find each other and vanish together. This was an extremely fragile state, where just a tiny change in balance could lead to two completely different scenarios. If everything were absolutely symmetric, the result would be very simple. Every particle of matter would find an antiparticle to pair with and annihilate. After a short time, the universe would be left with only pure radiation. No stars, no galaxies, no planets, no molecules, no biology. In that case, the universe would still exist, but only as a sea of energy containing no physical structures. In that scenario, the universe would have nothing to observe in the familiar sense. No points of light in the sky, no place for atoms to combine, no foundation for life. This is not a picture to be judged as bad or good, but simply a very cold result of a perfect balance between two sides. However, reality took a different direction. In that sea of chaotic interactions, the balance was not absolutely perfect, for some reason that science still does not fully understand. Matter slightly outnumbered antimatter. It was so small that, intuitively, the difference seemed almost negligible. The number often cited is, for every 1 billion particles of antimatter, there were 1,000,000,001 particles of matter. This means that in a very large group of particles, the two sides were almost equal, differing by exactly one particle. This ratio is like a neck-and-neck contest, where two armies step onto the battlefield with almost identical numbers, with one side having exactly one more soldier. If we imagine this as a strategic game on a universal scale, it was a game with no room for a draw. Each pair of particles that met would annihilate and turn into radiation. That process repeated across the young universe, in every direction. In a very short span of time, both sides gradually exhausted their forces in the same way. But whichever side had a little more would be left with particles that could not find an opponent. When the annihilation process nearly ended, most of the matter and antimatter had vanished. Radiation energy filled the expanding space. But the leftover matter particles, the ones that couldn't find a corresponding antimatter pair, still existed. They were not erased. They became the remainder of this ancient conflict. The surprise is that this surplus, incredibly small as it was per group of particles, was enough to create the entire world of matter as we observe it today. All the stars, all the galaxies, every gas cloud, every planet, every speck of dust drifting in space, originated from that very small number of extra particles left over after the initial annihilation. In that sense, every familiar physical structure is just a remnant. The human body, the ground, the seawater, the air, the objects within reach. They are all descendants of the particles that escaped death after an extremely fierce period of competition on a cosmic scale. Without that fragile surplus, there would be no matter to participate in any story thereafter. This perspective changes how we understand the origin of the physical world. Instead of seeing matter as an inevitable result, it can be viewed as the leftover portion after a nearly perfect balance. There was no pre-assigned function, no priority for one side. There was only a small asymmetry, but it was enough to tip the entire outcome in favor of matter. This asymmetry remains one of the great open questions of modern physics. Why the universe favored matter over antimatter by exactly such a tiny fraction still has no final answer. Theoretical models and experiments are still trying to understand the mechanisms that could have created that difference in the first moments after the Big Bang. Though the cause is not yet fully understood, the consequence of this imbalance is very clear. Once most of the matter and antimatter had annihilated each other, the universe entered a new phase. Radiation still dominated, but the surviving matter particles began to become the main characters for the next part of the story. They no longer faced the risk of being immediately wiped out by an equal amount of antimatter. From that point on, the direction of the universe's development changed. Instead of being a sea of pure radiation, containing no structure, no focus points, and no place denser than another, the universe now had scattered matter particles, tiny, few in number, but enough to participate in new, more sophisticated interactions. Those particles began to be governed by different forces. It was no longer just colliding and vanishing. Gravity, electromagnetism, and nuclear interactions gradually guided the way they combined, dispersed, and then gathered into initial forms of structure. All of those processes were based on the foundation of the small number of matter particles that survived the annihilation phase with antimatter. This can be seen as the end of the most chaotic era, but also as the starting point for everything familiar later on. From this step forward, matter had the chance to bind together instead of only existing for fleeting moments. Individual particles began to gradually move toward more stable, longer-lasting forms. As the universe continued to expand and the temperature dropped further, conditions became more favorable for the next step. The fundamental particles left over from the confrontation with antimatter began to bond, no longer just rushing about freely. From there, the first building blocks of atoms gradually formed in a universe that had become less violent than in its early beginnings. After the most violent early stages, the universe began to enter a different rhythm of change. Space continued to expand, but the temperature was no longer at a level that destroyed everything instantly. Against this backdrop, the particles that had appeared earlier, still moving very fast, began to have the opportunity to bond with each other in new ways. When the universe was only about 1 second old, the temperature had dropped enough for particles to slow down slightly. Not slow in the familiar sense of daily life, but slower compared to the previous stage of pure energy. Oppositely charged particles began to attract each other more strongly, and instead of being immediately pulled apart by violent collisions, they could maintain their bond for longer periods. In this context, the first atoms appeared. This type of atom was very simple, consisting of only one proton and one electron. That was hydrogen. Simple as it was, it became the foundation for most of the matter present in the universe thereafter. As conditions continued to change within the first few minutes, it wasn't just hydrogen that formed. A small portion of protons and neutrons combined to form helium, and a very tiny amount formed lithium. This period, lasting only a few minutes, was enough to establish the first trio of fundamental elements. Hydrogen made up the majority, helium came second, and lithium was present in a very small proportion. Later, all heavier elements would be born within the cores of stars or in stellar explosions. But in the early stages, only these three elements existed in significant quantities. Their appearance marked a clear transition in the history of the universe. Previously, there were only individual subatomic particles, frequently transforming between states of matter and energy. From here, the first stable structures at the atomic level began to emerge. The universe had taken another step from microscopic chaos toward the basic units of chemistry. However, the existence of the first atoms did not mean the universe had become clear. For the next several 100,000 years, space remained in a state very different from today. These early atoms existed alongside a vast amount of free electrons and high-energy radiation. Consequently, the universe was like a dense, bright environment that was nonetheless impossible to see through. One can visualize this period as a thick, pale soup where light was constantly scattered. Every time a photon attempted to travel, it quickly struck a free electron, changed direction, and was scattered yet again. Light had no chance to travel straight over long distances. Everything was obscured in a thick mist of electric charges. If an observer were placed in that era, Their vision would not reach far. There was no clear horizon, no definite shapes of objects. Any ray of light could only travel a short distance before being bent, absorbed, or scattered. The universe existed in a prolonged state of opacity. Even though energy and matter were present and blended together, this state lasted for about 380,000 years. During that time, all processes took place silently within the cosmic fog. Hydrogen and helium atoms gradually became more stable, but were still surrounded by a sea of free electrons. The complete combination of nuclei and electrons was not yet widespread. High-heat collisions still continuously broke apart newly formed structures. The fact that the universe was opaque during this stage explains why it is impossible to look directly back at the moment of the Big Bang using ordinary light. Light simply did not yet have a free path to carve a clear mark on space. Only when conditions changed deeply enough was this state finally relieved. As time passed, the universe continued to expand. The distance between particles increased. Energy density gradually decreased. The temperature continued to fall. Every step in temperature reduction brought a change in how matter and radiation interacted. Gradually, the likelihood of electrons binding firmly to atomic nuclei became higher than the likelihood of them being torn away by high-energy collisions. At a certain point, when the universe was about 380,000 years old, the balance tipped decisively. The temperature was low enough for most electrons to be captured by nuclei, forming neutral atoms. As electrons no longer drifted freely in large numbers, light was no longer scattered as intensely as before. At that moment, it could be said that the cosmic fog gradually cleared, not by an explosion of light, but through a process occurring across all of space simultaneously. Everywhere, neutral atoms formed, and the environment became transparent to radiation. Photons that were previously trapped in the milky soup could now move almost freely. This moment marked the first time light could run across the universe without being constantly blocked. The photons that escaped then continue to travel to this day, their wavelengths stretching gradually with the expansion of space. This is the oldest surviving light, carrying information about the moment the universe just became transparent. Historically, this was the end of a very special dark age. Not darkness due to a lack of energy, but darkness due to the inability to see through it. From this milestone onward, the universe gradually allowed observation through radiation. Light could travel far, carrying traces of the density, temperature, and distribution of matter at that time. As the first light began its long journey through space, matter itself had not yet formed stars or galaxies. The universe was mostly hydrogen and helium, distributed relatively evenly, with very small ripples in density. These ripples would later become the starting points for large structures. But at the stage of the first light, everything was still very simple and calm. From then on, light and matter entered a new relationship. Light was no longer trapped in an opaque environment, but became a tool to read back through the past stages. For matter, becoming transparent opened the conditions for gravity to work more effectively on small differences in density. Regions that were slightly denser began to attract more surrounding matter. Thus, the formation of the first elements, the prolonged period of fog, and the moment the universe became transparent are three successive steps in the same story. From pure energy, the universe created atoms. From an opaque environment, it gradually moved to a state that allowed light to travel far. And from that background of ancient light, the next steps in forming stars and large structures would begin to take place in the relative quiet darkness of expanding space. In the history of the universe, the death of a star is not a silent moment. It ends with a violent explosion of unimaginable proportions. When a sufficiently massive star reaches the end of its life, it can explode into a supernova. In an instant, the energy it releases can be trillions of times greater than the energy radiated by the sun. The brightness of that explosion can outshine an entire galaxy containing hundreds of billions of active stars. To envision it more closely, one could temporarily place Earth into that context. Though this is merely a comparison, if a supernova were to explode at a distance of a few dozen light-years, this planet would no longer be a safe place. The amount of radiation emitted would be enough to heat the atmosphere to the point where it is stripped away and dismantled. The protective layer around the Earth would be incinerated. X-rays and various types of high-energy radiation could penetrate deep into the surface, affecting even underground regions that are usually considered safer. In such a scenario, familiar forms of life could hardly survive. From a physical perspective, a supernova is an extreme event. It can wipe out everything across a vast region of space. But simultaneously, it is the birthplace of things that later become the foundation for rocky planets, atmospheres, oceans, and living bodies themselves. The death of a star is not just an endpoint, it is also a starting point for many new structures in the universe. A massive star lives most of its life as a stable nuclear reactor. In its core, light nuclei collide and fuse together, releasing energy. This energy creates outward pressure. Meanwhile, gravity pulls all that hot gas toward the center. When these two forces are in balance, the star maintains an almost constant shape for a very long time. Initially, the primary fuel is hydrogen. Hydrogen nuclei fuse to form helium. When most of the hydrogen in the core is consumed, the process moves into a new phase. Temperature and pressure rise high enough for helium to combine into heavier elements like carbon and oxygen. Everything continues to be held in a balance between the inward pull and the outward push. But no fuel source is infinite. When fusion reactions can no longer be maintained as before, the amount of energy produced decreases. The pressure from the core is not strong enough to resist gravity. From here, the star begins to slip from its stable state. The balance is broken. The core tends to contract, while the outer layers may react in different ways, depending on the mass of the star. For stars like the Sun or slightly smaller, the end is not a supernova explosion, but a quieter yet still extreme death. As the fuel in the core nearly runs out, the star swells up, becoming a red giant. Its size can expand to the point of swallowing nearby orbits. In the case of the solar system, the predicted scenario is that the Sun's outer layers could reach the region of Earth's current orbit. During the red giant phase, the outer layers of gas are gradually blown away into space, forming a thin and sparse shell. What remains at the center is a tightly compressed core. The size of this core is much smaller than the original star. By comparison, it might only be about the size of a planet like Earth, yet its mass is nearly that of the entire former star. The result is a white dwarf. It is a sphere primarily composed of oxygen and carbon, compressed to an extreme density. Atoms are forced much closer together than what is familiar in normal matter. The core of the star has lost its brilliant shell, now remaining as a white-hot mass that fades in brightness over time. From a size perspective, it can be said that the star's core shrinks to about 1/1,000,000th of its original size. That contraction does not create a dazzling explosion like a supernova, but it demonstrates the power of gravity when nothing is strong enough to resist it. For solitary star systems like the solar system, this is the common end. But not every star is lonely. Many stars exist in pairs, or in groups, orbiting each other in binary or multiple star systems. In those systems, the death of a single star can lead to much more violent scenarios. When a white dwarf lies next to another star, the exchange of matter between them can trigger new explosions with greater destructive power and more brilliant light. Before reaching those complex scenarios, it is necessary to return to the story of the constructive role of supernovas. When a massive star truly explodes, the layers of matter in the core are torn apart and hurled into space at immense velocities. In that moment, Special conditions emerge: extreme temperatures, terrifying pressures, and dense energy levels. It is the ideal environment for creating heavy elements. The initial Big Bang only produced the simplest elements, such as hydrogen, helium, and a very small amount of lithium. Heavier elements, such as carbon, oxygen, silicon, iron, gold, were not created in that primordial event. They were born in the hearts of stars and then perfected in the final moment when the star exploded. When looking at a gold ring, a rocky crust rich in silicon, or the amount of iron in human blood, their origins can be traced back to such explosions. The fragments of the exploded star are cast out, mixing with gas and dust in interstellar clouds. Then, over millions to billions of years, these clouds collapse under the influence of gravity, forming new generations of stars and planets. Earth is one of the products of that recycling process. The materials that make up the rocky crust, the metal core, the water in the oceans, and the atoms in the bodies of organisms all once existed somewhere inside dead stars. Those stars exploded, scattering their matter into space. And from those fragments, new planetary systems were born. From a cosmological viewpoint, a supernova is the link between the death of a star and the emergence of rocky planets, atmospheres, and every molecule that constitutes life. They possess both the capacity to destroy an entire region of space and to serve as the site for synthesizing and dispersing raw materials for future complex structures. In the narrative thread of the universe, the death of a star is therefore not just an end. It is part of a broader cycle where matter is continuously compressed, heated, broken down, and then recombined in new ways. From those events, subsequent generations of stars appear, carrying planets around them. And on some planets, the right conditions for life to develop gradually form. As we go deeper into binary star systems and more violent forms of stellar death, the picture of the universe's harshness will continue to expand. But its foundation remains here, in understanding that a supernova is both the period at the end of a star's life and the starting point for many new structures in space. In space, a star rarely lives in solitude. Many stars are born in pairs, orbiting each other in a slow dance lasting billions of years. From afar, they are just two circling points of light. But at a closer distance, the relationship between them can become extremely harsh. When one of the two stars grows old and runs out of fuel, it does not explode right away. In many cases, it contracts into a white dwarf. This is the leftover core, much smaller in size but still holding nearly all the original mass. An object with a mass close to that of the Sun but only about the size of the Earth. Its density is so great that a teaspoon of matter there could weigh tons. If its companion is still younger and has not run out of fuel, this disparity opens up a new process. The white dwarf's strong gravity begins to pull hydrogen and helium gas from the surface of the other star toward itself. This gas pours into a continuous stream, wrapping around the white dwarf in a thin, hot, and bright disk. On a human scale, it is very difficult to have a simple image for this process. One way to visualize it is to see the white dwarf as a being that is always hungry. It no longer produces its own fuel, but has the ability to suck fuel from its partner. Each new layer of gas pulled toward it makes it heavier, denser, and also more unstable. This process can last a very long time. Every second, only a small amount of matter is transferred. But over time, the total mass pulled in becomes a problem. Everything in the white dwarf is kept in balance by the confrontation between the inward pull of gravity and the outward push of internal pressure. When the mass increases beyond a limit, that balance begins to falter. From a seemingly peaceful binary star system, a fuse is being prepared very slowly. There is no countdown, no easily noticeable outward sign. There is only a tiny stellar core growing heavier by the day. waiting for the moment it can take no more. When the white dwarf nears that limit, what happens inside it changes completely. The matter in the core is primarily carbon and oxygen, compressed at an immense density. Under normal conditions, they can exist in a stable state. But when the mass exceeds the threshold, the temperature and pressure at the center skyrocket. At some point, the carbon inside begins to fuse simultaneously, not slowly in small regions, but almost the entire star accelerates its reaction. Rising temperature makes the reaction faster. A faster reaction makes the temperature rise further. This loop leaves the star with no time to self-adjust. The white dwarf at this point is like a thermonuclear bomb already assembled, just waiting for the triggering condition. When the carbon and oxygen reaction erupts, the entire core becomes a giant reactor. In a brief moment, the energy released is equivalent to about 20 billion megatons of explosives. This number is not for memorization, but to suggest the feeling that nothing familiar on Earth can compare. From astronomical distances, this explosion appears as a sudden flash of light that then fades. It is a Type 1, a supernova. Outwardly, it resembles many other stellar explosions. But the internal mechanism is very special. A white dwarf reaches a mass threshold and then incinerates itself in an unstoppable chain reaction. During the explosion process, most of the star's matter is torn apart and blasted into space at very high velocities. The previously compressed layers of carbon and oxygen are transformed. Many of them are cooked into heavier elements, including a large amount of iron. These streams of matter spread out for trillions of miles, carrying the ashes of the star throughout the surrounding space. Because the explosion mechanism is quite similar across many binary star systems, the peak brightness of Type 1, a supernovas, is relatively uniform. That makes them standard markers for measuring distances in the universe. But from the perspective of this story, they are also iron production factories operating in a single burst. The role of iron does not stop at being a post-explosion product. It is also the main factor related to the death of many stars. In a star's core, for most of its life, energy is created when light atoms fuse into heavier ones. This process creates both light and outward pressure, keeping the star from being crushed by its own gravity. For elements lighter than iron, fusion releases energy. But when the reaction produces iron, the situation reverses. Instead of releasing it, reactions involving iron need to absorb more energy to occur. This means if a star's core begins to accumulate too much iron, it no longer has any way to create new energy from thermonuclear fusion. The very moment a star enters the stage of producing iron in its core, physically, it has reached a limit. The iron core is like a dead object in terms of energy production. It no longer helps maintain pressure balance. Gravity continues to pull everything toward the center, but there is no longer any energy source strong enough to push back. This phenomenon does not only occur in Type 1, as supernovas, in giant stars, many times heavier than the Sun. The fusion process goes through many layers, from hydrogen to helium, then to carbon, neon, silicon, until an iron core is formed. When this core forms, the star is placed in the same predicament, sentenced sooner or later by the very type of matter it just created. The piece of iron in a frying pan, the iron bar in a door frame, or the layer of iron in the Earth's core all share a common history. Somewhere, long before they became familiar items, iron was once the core of a star, or the product of a stellar explosion. At a fundamental level, this is the matter associated with the final stage in the life of many bright, hot stars. The characteristic of iron, with its ability to hold energy instead of releasing more, breaks the chain reaction that keeps the star alive. When the energy from the core is no longer enough to support gravity, the outer layers of matter begin to collapse inward. In some cases, this collapse leads to another supernova explosion, violent in its own way. In a Type 1, a supernova, iron primarily appears as the product ejected after the white dwarf's explosion. Over millions of years, that iron can mix into gas clouds, participating in the formation of new generations of stars and planets. In massive stars, iron is the definitive end for the core's ability to maintain a stable state. Whatever the mechanism, iron always stands at the limit point. It marks the boundary between the phase where the star still has the ability to produce energy and the phase where everything is handed over to gravity. From then on, the next development is usually collapse, core compression, and more extreme explosions where elements heavier than iron are created. In the general picture of the universe, Type 1, a supernovas are both sources of light and sources of matter. They turn old white dwarfs into waves of energy and iron, spreading everywhere. Each time this happens, the surrounding space is marinated with a new layer of elements, ready for future structures. In other regions, massive stars are also silently reaching their own iron limits. When their cores are filled with this element, the story no longer stops at ejecting iron but also leads to the birth of heavier elements in explosions that are much more violent. In another phase of the universe, giant stars begin to become the main characters. These are stars tens, even hundreds of times heavier than the Sun. They are born with a great deal of fuel, but they also consume it at a breakneck pace. Their lifespan is much shorter than that of normal stars. One can imagine them as lamps that burn through their oil very quickly because they burn so bright and so hot. Inside such stars, the fuel-burning process does not stop at familiar levels like hydrogen or helium. When hydrogen is exhausted, the star switches to burning helium, and then sequentially produces carbon and oxygen. But because the mass is so great, the pressure and temperature in the core are high enough to continue pushing this process even further. The fuel continues to be cooked into neon, then silicon, and finally iron. If one could see through the shell, the internal structure of a giant star would resemble a multi-layered cake. The outermost layer is where the remaining hydrogen resides. Inside that is the helium layer. Deeper still is the carbon layer, then oxygen, neon, silicon. At the very center is the iron core. Each layer is like a Russian nesting doll, tucked into a larger one. Each ring represents a different fuel-burning stage. These progressively heavier elements do not drift away. They are accumulated and stacked upon each other in the heart of the star. These layers of matter are held by gravity. As if trapped inside a giant pressure cooker, everything still lies quietly there. There is not yet a mechanism to disperse them into space. This is the accumulation phase, where the universe silently prepares the ingredients for a decisive event. When the iron core appears, the story inside the star changes direction very quickly. Iron is a crucial milestone, because burning iron no longer releases energy. Instead of creating pressure to resist gravity, the iron core becomes like a heavy mass that only knows how to sink. From this point on, the star no longer has enough internal strength to maintain its previous state of balance. This imbalance leads to a process that happens extremely fast. The iron core, approximately the size of Earth, begins to collapse inward. The collapse time is only about a millisecond. In that very short span of time, the core size shrinks from the scale of a planet to a scale equivalent to an area the size of Manhattan, about a few dozen kilometers. The rate of contraction is at an unimaginable level. Matter in the core moves inward at about 1/3 the speed of light. All empty space is erased. Particles are squeezed closer together than in any familiar environment. The density of matter reaches a level trillions of times greater than the density of water. It is a state where a small block of matter could weigh as much as an entire mountain range. When the core reaches its compression limit, the collapse process is suddenly halted. The matter there becomes so hard that it is almost impossible to compress further. This stop creates a powerful rebound. Just as when a heavy object falls freely and is suddenly blocked, a shockwave spreads back outward. The energy released is enormous. Packed into a very short duration, that wave collides with the layers of matter surrounding the core. Those cake layers that the star built throughout its life are swept into a violent process. This is the moment that marks the boundary between a surviving star and a supernova explosion. The root cause began simply from the star reaching the usable limit of fuel in its core. As the shockwave spreads, it pulls the outer layers of matter along and compresses them once again, under conditions even harsher than before. Temperature and pressure skyrocket. In this environment, atomic nuclei are bombarded by a large number of neutrons. These neutrons are stuffed into the nuclei at very high speeds. At the nuclear level, reactions occur successively and almost instantaneously. Iron, which was already the end product of the fuel-burning process, is processed once more. It absorbs more particles, becoming cobalt, then nickel. Through such multi-step reaction chains, a small portion of matter continues to be built into even heavier elements, such as gold, platinum, and uranium. This entire manufacturing process happens very fast. It does not last for hours or years, but only for the brief duration of the explosion. Therefore, the amount of super-heavy elements created in each such instance is not very large. This is one of the reasons why gold and precious metals are much rarer than light elements. Nevertheless, explosions of this type are the only places in the universe with the conditions sufficient to create elements heavier than iron. Normally, in a stable, stellar core. Thermonuclear reactions are only favorable for building up gradually to iron. To pass that mark requires the extreme environment that only a supernova can provide. As the shock wave continues to push outward, the entire shell of the giant star is torn apart and hurled into space. The elements formed in the core and middle layers are no longer held tightly by gravity. They are released, mixing with surrounding gas and dust. The explosion remnants spread over time, forming massive clouds of matter. Inside those clouds are all kinds of elements, from hydrogen and helium to carbon, oxygen, silicon, iron, and even a small portion of gold, silver, platinum, along with many other heavy metals. The newly created matter does not clump together immediately. It drifts, expands, and merges into the interstellar medium. This process can last millions of years. On a longer timescale, these clouds, rich in heavy elements, can be compressed due to gravity or from collisions with other shock waves. When that happens, they become the birthplaces for new generations of stars, along with accompanying planetary systems. Matter that was once deep in the core of a giant star will be redistributed into many different structures. Thus, giant stars do not just end with an explosion. Before collapsing, they manage to build a multi-layered structure, storing heavy elements in the deepest part. In the final moment, the collapse of the core and the subsequent explosion is the mechanism that breaks that casing, releasing the layers of matter into space. The rare precious metals found later are only a small part of that matter, but they are clear traces demonstrating the role of giant star explosions in shaping the chemical composition of the universe. Each time such a star ends, the periodic table of elements is expanded a bit further in the interstellar environment. After the energy of the explosion gradually dissipates, the remnant at the center may remain in the form of a very dense neutron star, or in some cases, become a black hole. The collapsed core no longer shines as before, but what has been hurled outward continues to move, no longer belonging to the original star. The story of the death of a giant star therefore does not stop at the moment the explosion ends. It continues for a very long time, as the layers of matter thrown out merge into space and participate in new formation cycles. From such collapses, the chemical composition of the universe is enriched, ready for more complex structures later on. In the region of space around Jupiter, There is a moon that was once considered a cold and silent rock. In early blurry photos, it was just a small dot, with no sign of internal vitality. It wasn't until the Voyager 1 spacecraft flew by in 1979 that this picture changed completely. The images sent back showed that Io's surface was not smooth or dull. It was mottled with many colors: yellow, orange, brown, black, resembling a pizza covered with sauce and scorched patches. The dark spots on the surface are not impact craters or signs of erosion, but volcanic craters. From those points, gas and lava erupt high into the air, reaching heights of about 400 kilometers, equivalent to over 250 miles, before falling back to the surface. Io does not have a few scattered volcanoes. It is a world of volcanoes, with over 400 active ones, making it the most geologically active body in the solar system. This discovery forced old models to revise the assumption that all small moons had cooled and become motionless. The natural question that arises is, why can a moon so small be so active? It is not large enough to retain much heat from its formation era, and it lacks a burning nuclear core like stars. The energy source must come from a different mechanism, tightly linked to the giant planet it orbits. Io's orbit around Jupiter is not perfectly circular. It is slightly elliptical, just enough for this moon to be continuously stretched and then released within Jupiter's very strong gravitational field. As Io moves closer, the gravitational pull increases, and the entire celestial body is elongated. As Io moves further away, the pull decreases, and it tends to return to a circular shape. This process repeats, creating inhaling and exhaling pulses that are very slow but extremely powerful. Io's surface is therefore never still. There are estimates suggesting the ground there can bulge and subside by hundreds of feet in just a few days. One can simply imagine rubbing two hands together repeatedly. When two dry surfaces rub against each other, the temperature rises inside without needing an external flame. On Io, the rubbing happens not between two hands, but between the gravitational field of a giant planet and the rock mass of a small moon. Energy from this tidal force converts into heat, warming and melting the rock inside Io. When the rock beneath the surface becomes liquid, it finds a way out through cracks and conduits, creating eruptions of lava and gas. Gravity here does not just keep Io orbiting Jupiter, it also acts as an engine, constantly kneading the interior of the celestial body, maintaining geological activity at an extremely intense level. This mechanism shows that gravity is not just a pull, keeping things together. Under certain conditions, it is also an energy source that can activate and sustain an entire volcanic system. From a moon considered dead, Io became a clear example that small worlds do not necessarily have to be cold and silent. A bit further away, around Saturn, there is a moon that outwardly appears to be the opposite of Io. Enceladus is small, bright, and ice-covered, looking like a frigid sphere with nothing special about it. At a quick glance, one might easily feel this is a completely frozen place with no internal movement. But measurements from the Cassini spacecraft revealed a different story. As Cassini flew near Enceladus's south pole, its instruments recorded plumes of matter erupting from the surface. It wasn't red-hot lava, but liquid water and water vapor shooting straight into the vacuum of space. As it jetted out of the icy shell and encountered the harsh, cold environment, the water immediately froze into tiny ice crystals, creating an icy mist spreading around the moon. These ice particles do not disappear. Some fall back to the surface, adding to the existing ice layer. Others drift further away, participating in the formation and maintenance of a thin ring around Saturn called the E-ring. Over time, the particles in this ring should have fallen away or drifted elsewhere. Yet, observations show the ring still exists. The water plumes from Enceladus are the constant supply line, replenishing ice particles for the ring and keeping it from vanishing. Unlike Io, where volcanoes erupt lava, Enceladus can be seen as possessing cold volcanoes instead of molten rock. Here it is, liquid water and water vapor being pushed out through cracks in the icy shell. This phenomenon is known as ice volcanoes, or cryovolcanism. Despite very low surface temperatures, there is still enough heat beneath the thick ice to keep some of the water in a liquid state. These plumes do not appear randomly. They are linked to surface structures, often called tiger stripes. Long, dark, crisscrossing fractures near the South Pole. These cracks constantly open and close, affected by tidal forces as Enceladus orbits Saturn. Each time the moon is stretched, the cracks widen, allowing water and vapor from below to escape. When the pull decreases, they close somewhat, regulating the rhythm of the eruptions. Detailed measurements indicate that beneath the ice layer lies a vast liquid water ocean, not just an isolated pocket of water. The water there is not pure. It contains salts, similar to seawater on Earth, and has traces of complex organic compounds. Heat from tidal forces, liquid water, salt, and organic matter coexist in an environment well shielded from the vacuum and harsh radiation outside. This is a combination that modern biology considers very noteworthy. On Earth, places with liquid water, an energy source, and organic molecules are often favorable environments for complex chemical processes, and even for life. Therefore, Enceladus was quickly placed in the group of locations with a high potential for harboring some form of life in the solar system, even if it is in the form of simple microorganisms in the dark, deep sea. From this perspective, the water plumes erupting from Enceladus's south pole are not just a beautiful phenomenon. They are like samples fired into space, carrying information about what is happening in the ocean hidden beneath the ice. Flying through these plumes allowed probes to collect data on the internal chemical composition without having to drill through the thick ice. In the same solar system, two small moons exhibit two different types of volcanic activity. Io is scorching, erupting lava and gas, fueled by Jupiter's intense pull. Enceladus is cold and ice-covered, erupting water and ice, stirred by Saturn's tidal forces. Both show that the internal energy of a celestial body comes not only from radiation or nuclear reactions, but can also come from regular deformations caused by gravity. Looking closely, these eruptions are localized, explosions, much smaller than supernovas or distant cosmic radiation bursts. But within the scope of the worlds where they occur, they can renew the surface, pump in energy, and even create suitable environments for complex processes to take place over very long periods. From icy moons and celestial bodies once thought to be dead, these activities open up more questions about places that might be silently sustaining some form of life right in the neighborhood of the solar system. That is a magnetar. In essence, this is a form of neutron star, but with a magnetic field so strong it makes all familiar standards seem tiny. Its magnetic field can be about 1,000 trillion times stronger than the magnetic field of the Sun. From afar, it is just a small speck of light, but inside is an extreme environment almost impossible to imagine through daily experience. The size of a magnetar is not large. Its diameter is only about a few dozen kilometers, equivalent to a small city or a large asteroid, approximately 10 miles. Nevertheless, its mass is greater than that of the Sun. This means the entire previous giant star has been compressed into a very compact sphere. Every cubic centimeter inside carries a density of matter that no experiment on Earth can replicate. A common comparison used is a teaspoon of matter from a magnetar. If one could scoop such a small spoonful and bring it near Earth, its mass would reach trillions of tons. That is a number far exceeding the total mass of all buildings in a large city. One could also imagine compressing a star into the volume of an area the size of Manhattan, with its entire mass still retained. These images are not perfect, but they help illustrate the extreme nature of the object. Due to such density and magnetic fields, magnetars are often called by many scientists one of the scariest objects in the galaxy. Not because it actively attacks, but because simply by appearing in a sufficiently close range, its existence is enough to cause irresistible effects. It is an almost invisible threat in the darkness, but it carries numbers that exceed all familiar standards. Earth's magnetic field is strong enough to orient a compass needle and keep charged particles from the solar wind from directly attacking the surface. A magnetar's magnetic field is so much stronger that familiar examples become too small. If a spacecraft approached within a few thousand miles, this magnetic field would begin to interfere with everything made of metal, circuits, and even the human body. At such a distance, every credit card, hard drive, magnetic tape, and data stored using current technology would be wiped clean. Small metal objects could be pulled away from their original positions, like paper clips being strongly attracted to a very large magnet. Metal jewelry would no longer rest peacefully on the body but would tend to be yanked violently along the magnetic field lines. Biological bodies operate based on very small electrical signals between nerve cells and the heart muscle. In an excessively strong magnetic field, these signals can no longer maintain stability. The heartbeat could become disordered and then stop altogether, not because of collision or temperature, but because the internal electrical signals are disrupted. At even closer ranges, the magnetic field is strong enough to distort the orbits of electrons around nuclei. The atomic structure of matter could be stretched and then torn apart. Such a death, if it occurred, would not come from fire, from collision, or from visible radiation. It would come from the magnetic force penetrating deep into the very structure of matter. This shows that the magnetic force in the universe, when in an extreme state, can become a force as powerful as any physical explosion. In the farthest reaches of the observable universe, explosions occasionally appear that are so bright they outshine an entire galaxy. They do not last for years or even hours. They flare up for a few seconds and then fade, like a very brief blink on the cosmic screen. Yet their energy traces are recorded for a long time. These events are known as gamma-ray bursts. They occur when a massive star, several times the mass of the Sun, reaches the final moments of its life and collapses. In that instant, the star does not merely shine brighter than usual. It releases more energy than the Sun produces in its entire 10 billion-year lifespan, all compressed into just a few seconds. If a gamma-ray burst were close enough, its light could be seen with the naked eye from Earth, even if it were billions of light-years away. This means that, for a brief moment, a single point in the sky could shine as brightly as, or even brighter than, its host galaxy. It is not because the galaxy has dimmed, but because the explosion surpasses all other light sources. It can be visualized as a cosmic blowtorch. Instead of shining equally in all directions, it fires two narrow, concentrated beams of energy, like two searchlight beams piercing through space. If any planetary system accidentally stood directly in the path of one of these two beams, it would face an enormous amount of radiation in a very short time. On the energy scale of cosmic explosions, gamma-ray bursts sit at the very end. At the highest limit, no type of electromagnetic radiation carries more energy per photon than gamma rays. This is not intended to create drama, but to set a clear milestone. When discussing extreme explosions, this is the highest point nature can reach based on what is currently observed. Behind those violent flashes of light is a silent process of collapse. When the nuclear fuel inside a supermassive star is exhausted, its core no longer has enough pressure to resist the gravitational pull created by its own mass. The core begins to shrink. The outer layers of matter collapse inward, crashing, compressing, and releasing even more energy. Under these conditions, gravity wins completely. No other force is strong enough to provide balance. A new black hole forms at the very center, where the density becomes so extreme that nothing, not even light, can escape if it comes too close. The outer components of the star are pulled into a spiral toward the shrinking core, creating a disk of superheated matter swirling around the young black hole. From the region near the black hole, two concentrated beams of energy are fired in nearly opposite directions, perpendicular to the plane of the matter disk. For a few seconds, these two beams carry most of the star's remaining energy. This is the gamma-ray burst that telescopes record. One does not need to see the black hole directly. Catching that flash is enough to know that a new black hole has just been born very far away. The difference between observing an old black hole and this specific moment lies in timing. Stable black holes are usually identified indirectly, through the motion of surrounding stars or the X-rays emitted from matter they gradually consume. In a gamma-ray burst, it is the very first minute. It is the moment the formation process takes place, at its highest energy, before the system enters a more settled state. Thus, a gamma-ray burst is not just a single explosion. It is a direct bridge between the end of a star and the birth of an extreme gravitational object. The death of a supermassive star and the emergence of a black hole are not two separate events, but two sides of the same process. As astronomers survey the sky with gamma-ray telescopes, each flashing signal is a notification. In a very distant place, a giant star has just reached its end, and a new black hole has just appeared. These signals are recorded hundreds of times each year, most coming from regions of the universe billions of light years away from Earth. However, the next natural question is, what would happen if such an event occurred much closer, not at the edge of the observable universe, but in the galactic neighborhood of our own solar system? In that case, the immense energy compressed in a gamma-ray burst would not just be a number on a chart. Estimates show that if a gamma-ray burst occurred at a distance of about 100 light-years and one of its two energy beams pointed directly at Earth, the side of the planet facing the beam would face an amount of energy equivalent to detonating a 1 megaton nuclear bomb on every square mile. This figure is provided to give the listener a frame of reference, not to describe specific consequences in detail. In such a situation, gamma radiation would interact strongly with the atmosphere, stripping away molecules and disrupting the planet's natural protective layers. Sunlight, which is usually the source of life, could then become a source of destruction, as ultraviolet rays would no longer be filtered as before. Complex life on the surface would have little chance of long-term survival after such a direct hit. Importantly, these scenarios are presented as the upper limit of risk, not as a forecast. The gamma-ray bursts currently observed mostly come from distant galaxies. Stars large enough to produce them are not numerous, and the probability that a narrow energy beam would align perfectly with Earth's direction, while also being within a dangerous distance, is very low. Space telescopes record an average of several hundred gamma-ray bursts per year, but all are very distant. Each signal is just a blinking dot on a star map, accompanied by information about position and time. Then it vanishes. On the ground, there are no noticeable changes accompanying these detections. The explosion occurs, spreads, and then only light remains, stretched and weakened by the enormous distance. Even so, knowing that explosions at this absolute level exist is enough to reset one's sense of safety. The universe is not a quiet, empty space. It is an energy system with many layers, containing processes that reach the very limits allowed by physics. Life on a small planet, with a thin surrounding atmosphere, depends greatly on not being in the direct path of those energy beams. From extreme explosions at the edge of the universe, the story gradually returns closer to home. It does not necessarily take a gamma-ray burst at a distance of 100 light-years to create a risk for Earth. Right within this planetary system, there is already a massive, more stable source of energy. Yet one capable of causing significant upheavals if conditions change. That is the star at the center of the system, which all orbits revolve around. In daily life, the sun appears as a stable disk of light in the sky. Light rises and falls predictably. Season follows season, and days pass quite steadily. From that experience, a familiar image gradually becomes an illusion of gentleness and stillness. It feels like an unmoving backdrop for all activity on Earth. At the physical level, the picture is very different. The sun is a massive ball of plasma where matter is always boiling and moving. Inside, currents of hot gas rotating at different speeds create complex magnetic field systems. These magnetic field lines constantly twist, break, reconnect, and deform. On a human scale, the level of that change is difficult to fully envision. The sun's magnetic field is strong enough to encompass the entire solar system. It does not just hold the planets in orbit through gravity, but also dictates how charged particles move in the surrounding space. Among the phenomena created by this system, a coronal mass ejection, or CME, is the most powerful type of outburst. This can be seen as the most formidable weapon the central star possesses. Even though it is just a natural consequence of magnetic activity, when a CME is mentioned, it is often confused with a solar flare. These two phenomena are related but not identical. A solar flare is a quick burst of energy, like a powerful but short-lived tornado. A CME, by contrast, is like a sustained superstorm. It does not just shine, it hurls a massive amount of matter outward. In a major CME event, the sun can cast tens of billions of tons of plasma into space. This amount is equivalent to the mass of millions of large buildings combined. That matter does not fall back. It is swept along magnetic field lines and fired straight out. Its speed can exceed 1 million miles per hour. To visualize it easily, imagine a giant cloud thrown from the sun's surface. This cloud is not water vapor, but charged particles carrying their own magnetic field. If its direction of travel coincides with Earth's position in its orbit, the cloud may take anywhere from a few dozen hours to a few days to reach the planet's vicinity. Underneath these phenomena is a simple process. The magnetic loops on the sun's surface short circuit. When the magnetic structure changes suddenly, the accumulated energy is forced to release outward. Part of the energy radiates as light. The rest carries the plasma with it. The result is a storm of magnetism and matter traveling across interplanetary space. Without any technological systems, a passing CME would simply be a fluctuation in space. Earth has experienced many such events throughout its long history. The problem only arises now that a form of civilization has appeared on the planet's surface that is almost entirely dependent on electricity and communication. When a CME cloud reaches the region around Earth, it does not directly incinerate everything. Earth's magnetic field acts as a shield, bending the path of the charged particles. However, the very interaction between the Earth's magnetic field and the incoming plasma creates powerful induced currents in the atmosphere and within the ground. These currents can spread into long conductors, such as power transmission lines and cables connecting stations. At a sufficient magnitude, they overload equipment, melt coils in transformers, and cause the entire system to become unstable. Once key nodes are damaged, the power grid of a region, or even an entire continent, can shut down simultaneously. In orbit, satellites also suffer heavy impacts. High-energy particles damage components, disrupt signals, and shorten the lifespan of the entire system. The loss to the satellite network alone could reach hundreds of billions of dollars. But the monetary figure is only an indirect description. Behind it lies navigation, communication, weather forecasting, and the entire chain of services based on data from space. If a major CME hit Earth in the current context, the consequences would not stop at a few local power outages. Estimates show that total property damage could reach several trillion dollars. This would be accompanied by the potential for widespread long-term power outages, loss of internet connectivity, and disruption of GPS and phone networks. When the power supply is cut, many other systems stop as well. Water pumps, cold storage, traffic lights, factories, and transport vehicles dependent on energy charging are all affected. Hospitals would be forced to rely on backup sources for a limited time. Logistics systems supplying food, medicine, and fuel would face difficulties. Modern life, which relies on a steady flow of electricity, could be pushed back to the simpler levels of decades ago. This threat differs from gamma rays or supernova explosions in that it does not kill people immediately. There is no wall of fire sweeping across the planet's surface. Instead, it attacks the foundation upon which modern society relies: electrical infrastructure, information, and coordination. The mere temporary suspension of those infrastructures is enough to shake the inherent sense of safety. In recorded history, very large CMEs do not occur constantly. Statistical models suggest that such extreme events might recur on a timescale of several hundred years. The average interval between occurrences is estimated at about 500 years. Though the exact value remains highly uncertain, there have been times when powerful CMEs passed near Earth's orbit without causing direct damage, simply because their path was slightly offset from the planet's position. In the early 2000s, one such major outburst was recorded, but its most intense part missed, not hitting the area where Earth was in its orbit. This can be seen as a near miss, occurring in silence for most inhabitants on the ground. From the perspective of cosmic time, a major CME aligning perfectly with Earth is not a question of if, but rather an event within a chain of possibilities that will arrive over a long enough period. In the time between such events, technological civilization continues to expand and increase its level of dependence on vulnerable systems. What remains is the context: a small planet orbiting a central star that is always active. On the surface of that planet, billions of humans build layers of connections, devices, and interlocking networks. All exist together in a period of relative peace, situated between the sun's major outbursts. Knowing the scale of those eruptions might change one's sense of stability slightly, not to create panic, but to recognize that the quietude of daily life is taking place within a vast and ever-moving system. Against that backdrop of movement, the sun continues to shine steadily, while silently accumulating energy for the next outbursts. Seen from a great distance, the story we have followed so far might look like pure chaos. A universe starting from an almost invisible point. Matter and antimatter colliding and vanishing. Stars building heavy elements and then tearing themselves apart. Beams of gamma rays flashing for a few seconds and disappearing. The sun occasionally throwing clouds of plasma into space. At first glance, these are separate acts of violence scattered across billions of years. But if one slows down and connects them, a different picture begins to appear. What seems like disorder starts to look more like a system that constantly regulates its own energy. The Big Bang, in that sense, was not only an explosion that began everything, it was also the first act of distribution. Energy that had been compressed into a region smaller than an atom was suddenly given more room. Space expanded at a rate completely outside human experience, and temperatures that had been high enough to erase every structure began, very slowly, to fall. Inflation did not create stars or galaxies. It simply stretched the initial state so that later, gentler processes would have somewhere to unfold. It is a pattern that will repeat, intense episodes that at first seem destructive, but that open the door for more stable phases. As the universe cooled, another invisible regulation took place. Energy crystallized into particles, and with it came antimatter. For a short time, Matter and antimatter existed almost in perfect balance, only to annihilate each other and return to radiation. It was a brutal process. Almost everything that appeared was erased almost immediately, yet it was precisely this near-perfect cancellation that left behind a tiny remainder. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. That almost negligible surplus is what remained after the storm. It became the raw material for all future structures. A vast, chaotic interaction ended not in nothingness, but in a thin layer of matter spread through space. On larger scales, gravity took over as the main regulator. Its strength could have led to two very different failures, a universe too empty or a universe too collapsed. When cosmologists change the value of gravity in their simulations, those are the two most common outcomes. Either matter never gathers enough to form galaxies, or it collapses too quickly, falling into dense regions and dark holes. Our universe followed a third path. Gravity was strong enough to pull gas together and create stars, but gentle enough to allow the overall expansion of space to continue. It is another form of managed violence, attraction that gathers, but not so much that it erases every gap. Inside stars, the same balance appears in miniature. For most of their life, they exist as a compromise between inward pull and outward pressure. Nuclear reactions in the core push outward. Gravity pulls everything inward. When those two forces are in equilibrium, a star shines steadily for millions or billions of years. Only when fuel is exhausted does the balance fail. Then, the calm and apparently stable star reveals what had always been hidden: the enormous amount of energy stored in its core. A supernova is the most visible sign of that stored energy being released. In a very short time, a star can outshine an entire galaxy. Matter that had been compressed deep in the core is thrown into space at immense speed. Layers that once lay quietly stacked are crushed, heated, and transformed. And yet, from a cosmic perspective, this extreme event is not just destruction. It is a recycling act. Light elements forged slowly during the star's life are converted into heavier ones. Carbon, oxygen, silicon, iron, and even a small share of gold and platinum are created and ejected. The violence of the explosion is the only way those elements can leave the star and become available for future planets. In binary systems, the regulation becomes even more precise. A white dwarf patiently steals matter from its companion, gaining mass grain by grain. For a long time, nothing dramatic happens. Then, when it crosses a critical threshold, the balance ends abruptly. The star ignites in a thermonuclear runaway and destroys itself in a Type Ia supernova. From afar, it looks like another bright point appearing and fading. Up close, it is a clear demonstration of how a slow process can prepare a sudden release. Matter is compressed until it can no longer endure its own density, and then everything is returned to space in one burst. Beyond that, even more compact remnants continue the pattern. Neutron stars and magnetars are what is left after some giant stars collapse. They are small in size, but they hold more mass than the Sun. In them, gravity has pushed matter to the edge of what it can be. At those densities, a teaspoon of material would weigh trillions of tons. The magnetic fields that arise there are so strong that, at a close distance, they can affect atomic structure itself. The regulating mechanism here is no longer heat or pressure in the usual sense, but the ultimate limits of matter under gravity. Gamma-ray bursts sit at the far end of this sequence. When a supermassive star collapses and a new black hole is born, the remaining energy is not spread evenly in all directions. It is focused into two narrow jets. For a few seconds, those beams radiate more energy than the Sun will emit in its entire lifetime. They are extreme expressions of concentration and release. Most of the time, They occur so far away that their effect on us is only a faint signal on a detector. But even when distant, they remind us that the universe often hides its most intense processes in very short, very focused moments. Closer to home, the sun repeats the same pattern on a smaller scale and over shorter timescales. Its magnetic fields twist and tangle, storing energy in invisible loops. When those loops break and reconnect, a coronal mass ejection can occur. Tens of billions of tons of plasma are thrown out into space, dragged along by their own magnetic field. This is not the end of the star, but a local rebalancing. Energy that had been stored in the magnetic structure is suddenly expelled. The sun remains, but its field lines are rearranged, its surface patterns reset, seen one by one. These events look like separate catastrophes. A universe inflating too fast to understand, particles colliding and vanishing, stars exploding, magnetars stretching matter to its limits. Gamma-ray beams briefly outshine all other light. Clouds of solar plasma sweeping across space. But when placed on the same line, they can be read differently. They are steps in a long process in which energy is always seeking a more spread out, less concentrated state. Compression and release follow each other. Matter gathers, collapses, explodes, and then drifts. The apparent violence is the mechanism by which the universe moves from extreme, unstable conditions toward broader, quieter forms of order. From this perspective, the cosmos is not a stage of random disasters. It is a system that uses extreme events to adjust itself. Each explosion, each collapse, each outburst is a way of redistributing energy and matter. The result, over time, is not a burnt-out space but one that contains stars with steady light, planets with stable orbits, and long periods of relative calm. The story of violence and the story of stability are not two different stories. They are the same process, viewed at different distances and on different timescales. When looking at the whole sequence, another feature becomes clear. The universe not only regulates its energy, it does so within a corridor that is extremely narrow. A small change in the initial conditions, a slightly different setting in the basic numbers, and the story would have taken a very different turn. It is not that everything is perfectly adjusted for safety. It is that many things sit just far enough from failure to allow complex structures to exist for a while. Gravity is the first example of this corridor. In simulations, when its strength is reduced, matter drifts apart too quickly. The universe expands, but almost nothing interesting happens. No galaxies, no stars, no planets. Just a thinning fog of particles sliding away from each other. When gravity is made stronger, the opposite occurs. Matter clumps so fast and so violently that many regions collapse into black holes before stable structures can form. In both cases, the outcome is simple: a universe with very few places for complexity to arise. Only in a narrow band between those two extremes do we see the filamentary web of galaxies that telescopes actually observe. The early imbalance between matter and antimatter is another step in the same corridor. If their numbers had been exactly equal, they would have erased each other completely. The result would have been a universe filled with radiation, with no atoms and no building blocks for later structures. If the imbalance had been much larger, matter would still exist, but the entire thermodynamic history would be different. Radiation levels, densities, and timescales would not match the ones that eventually led to the first stars. Instead, what actually happened was a very small offset, one extra particle of matter for every billion particles of antimatter. The universe did not choose a clear victory for one side. It moved just far enough from a perfect draw. The same narrowness appears in the life cycles of stars. If stars were much smaller or much larger on average, or if nuclear reactions worked under very different thresholds, Their role as long-lived energy sources would be compromised. Some stars already burn through their fuel too quickly and end in violent supernovae after only a few million years. Others, like the Sun, shine steadily for billions of years. If the basic rules had produced only the first category, there would be less time for any complex process to unfold on surrounding planets. If only the second existed, the periodic enrichment of the universe with heavy elements would be slower. Instead, there is a mixed population, stars that live calmly and stars that die explosively, together creating both continuity and renewal. On more extreme scales, gamma-ray bursts mark the upper edge of what a collapsing star can do. They are not frequent, but when they happen, their beams carry an impressive amount of energy even by cosmic standards. Calculations show that if such a burst occurred at a distance of about 100 light-years and its beam pointed directly at Earth, the consequences for the planet's surface would be severe. The atmosphere would be altered, and complex life would struggle to survive in the long term. That scenario sits on the far side of the corridor. Yet, the bursts we actually observe happen at distances of billions of light-years. Their light reaches our instruments, but their physical effects do not reach us. They mark the limit of what is possible, while our planet orbits quietly far away. The Sun's coronal mass ejections follow the same pattern on a local scale. They show that our own star is capable of launching storms that, if aligned exactly with Earth and strong enough, could disrupt modern civilization. Power grids, satellites, and communication systems are vulnerable to the induced currents that such events can generate. Historical records and modern observations indicate that very large CMEs do occur. Some have missed Earth by a small margin. Others have hit, but at times when technology was less spread out. Here too, the corridor is visible. Our technical systems grew during a relatively calm interval in the Sun's activity, not during a sequence of closely spaced major impacts. Earth carries another layer of narrow protection in its magnetic field. That field is strong enough to divert most of the charged particles from the solar wind and from smaller solar storms. Without it, those particles would strike the atmosphere much more directly. Radiation levels at the surface would be very different. Yet the field is not impenetrable. During strong storms, some particles still enter near the poles, creating auroras and small fluctuations in technology. Once again, the condition is not absolute safety. It is a partial shield that keeps conditions within a range that living systems can tolerate over long periods. There is also the quiet fact that Earth's motion has been stable enough for climate patterns to persist within certain bounds. Over geological timescales, the planet has experienced ice ages and warmer periods, but it has not frozen solid forever or boiled its oceans away. Its rotation, orbit, and tilt have varied within limits, but not so much that the basic cycle of day and night, seasons, and moderate temperatures was destroyed. From a cosmic perspective, this too is a corridor, wide enough to allow change, but not so wide that the system falls apart. When all these layers are placed side by side, the strength of gravity, the early matter surplus, the way stars live and die, the distance to the most violent explosions, the behavior of our own star, the shielding effect of Earth's magnetic field, and the relative stability of its motion, a pattern emerges. There is no sign of a universe that guarantees safety. Gamma-ray bursts still occur. Magnetars still exist as dense reminders of how far matter can be pushed. The Sun still launches storms. The corridor does not remove risk. It simply sets ranges within which risk is survivable for long stretches of time. This is why one can say that the universe does not offer safety by strength, but by balance. It does not build invulnerable shelters. It allows islands of relative calm to form between extremes. Stars are not unbreakable. They are long-lived only as long as fuel and gravity remain in temporary truce. Planets are not sealed off from cosmic events. They are protected just enough, just often enough, to keep their conditions within a livable band. The corridor is fragile, but it is wide enough for life and complexity to appear and to persist for a while. Thinking of it this way, existence on a small, rocky world orbiting an ordinary star becomes something very specific. It is the result of many parameters landing inside narrow windows rather than outside them. A slight difference in how the early universe expanded, in how matter and antimatter balanced, in how often giant stars explode nearby, or in how active our star is. And the same laws of physics could have produced a very different environment. There would still be a universe, still energy and matter, but not necessarily a place where long stories are possible. The corridor is not a guarantee, and it is not eternal. It is a temporary alignment of conditions. On one planet, during one phase in the life of one star, in one galaxy. Yet within that alignment, there is room for oceans, for atmospheres, for continents, for fragile biological chemistry, and for the quiet act of looking up and noticing that the night sky is full of past explosions. The same processes that threaten from far away are the ones that make the elements in the ground, in the air, and in every living cell. Balance, not invincibility, is what has allowed this to be true for as long as it has. In the middle of all these processes, Earth moves along its orbit in a comparatively calm region of space. It circles an ordinary star in a regular path, at a distance that does not make headlines in any catalogue of extremes. There are no nearby magnetars twisting space with their fields. No recent supernova scars appear in the sky as expanding shock fronts within a few light years. Gamma-ray bursts are recorded as distant flashes on detectors, not as events that leave traces in the atmosphere. From this position, the violence of the universe is mostly something that arrives as faint signals and passing data. The star at the center of this system is active, but it is not in the most unstable phase of its life. It boils and rearranges its magnetic fields. It occasionally launches coronal mass ejections into space. Yet, most of those clouds of plasma travel into empty regions, disperse, or pass by. Earth's orbit does not sit directly in their path most of the time. When a cloud does arrive, the planet's magnetic field deflects a large part of the charged particles, guiding them toward the poles and turning some of the energy into auroras. The same process that could, at a different scale, disrupt systems over an entire continent is usually reduced here to structured light in the upper atmosphere. Seen from the surface, this filtering is almost invisible. Days follow one another with sunlight that seems constant. Nights are dark enough for stars to appear. The transition between day and night is smooth. There is no sign that streams of particles are being bent and slowed before they reach the ground. The calmness of that rhythm, however, depends on many things not happening. No nearby star collapsing into a black hole. No intense beam from a gamma-ray burst crossing the planet's orbit. No magnetar approaching within a dangerous range. Earth's atmosphere adds another layer of quiet. It absorbs and scatters a large portion of high-energy radiation coming from space. It is thick enough to burn up small objects entering at high speed, turning them into brief streaks of light instead of impacts. From above, it is just a thin shell of gas hugging the surface of a rocky planet. From below, it is the medium through which every ordinary sound travels. Wind, voices, water, machines. It is not a shield designed for safety. It is a byproduct of geological and chemical processes that, for now, also serves as a soft barrier between the ground and the vacuum. The orbit itself is another factor. Earth moves in a path that is stable enough for seasons to repeat and for climate patterns to vary within certain ranges rather than jumping between extremes. Over long timescales, temperatures rise and fall. Ice advances and retreats. But the planet does not alternate between being completely frozen and completely molten in rapid cycles. There is time for oceans to persist, for continents to erode slowly, for biological processes to accumulate layer over layer in the rocks. None of these conditions remove the underlying harshness of the universe. The Sun remains a nuclear reactor with layers of hot plasma. The galaxy continues to host massive stars that will, at some point, end as supernovas, scatter heavy elements, or form black holes. In distant regions, magnetars spin and gamma-ray bursts flare. The fact that these events do not currently occur within a short distance of Earth is not a sign of special protection. It is a matter of location and timing. From another point of view, Earth can be described simply as a place where many extreme events are far enough away to be part of the background. The intense phases of the universe are not absent. They are just happening elsewhere, at other coordinates, or in other epochs. What remains here, at this address in space and time, is a reduced version of that activity, sunlight at a stable level, variations in the solar wind that are noticeable but not catastrophic, a steady rain of cosmic rays moderated by magnetic and atmospheric layers. This does not make the planet unique. Across the galaxy, there may be many worlds arranged in similar positions, orbiting stars with comparable behavior. In regions where supernovas are not frequent, Earth is one example among possible many. What gives it the appearance of a shelter is not a special status, but the combination of its distance from major sources of disruption, the current age and state of its star, and the filters created by its own internal processes. The quiet is also not permanent. Over timescales much longer than human history, the Sun will change. It will exhaust its hydrogen fuel, swell, and alter the conditions in the inner system. Orbits can slowly shift. External events, such as the passage of a massive star at a moderate distance or a rare nearby explosion, remain possible. The shelter is temporary by definition, because no configuration in the universe is frozen forever. Yet this temporariness does not have to be read as a threat. The durations involved are immense compared to the length of a human life, or even the lifetime of a civilization. For now, the combination of factors that produce this relative calm continues to hold. The Sun's output fluctuates within narrow bands. The planet's magnetic field still operates. The atmosphere remains in place. Gamma-ray bursts and supernovas continue their work at distances where they are signals, not impacts. In this sense, Earth is a pause in the larger story of energy being concentrated and released. It is a location where, at the current moment, matter is arranged in a way that permits long, uninterrupted periods of moderate conditions. There is no guarantee that this arrangement will last indefinitely, but there is also no immediate sign that it is ending. It is simply one of many temporary configurations the universe allows, in which the background noise of cosmic violence is low enough for more delicate processes to unfold near the surface of a small rocky world. From the ground, this can be hard to see. Daily experience is built on local weather, local landscapes, and personal events. The constant presence of the wider universe is easy to ignore, but if one places Earth back into the context of supernovas, magnetars, gamma-ray bursts, and solar eruptions, its role becomes clear. It is not exempt from the rules. It is a small, relatively quiet zone inside a system that, at larger scales, is always adjusting itself through dramatic events. The shelter it offers is real, but it is defined not by walls that cannot be crossed, but by distances, timing, and layers of partial protection that, for now, are enough. If we move our focus slowly away from the details, the picture changes once more. The ground, the atmosphere, the familiar shapes of land and water begin to recede. Earth becomes a curved surface with a thin line of air around it. Clouds drift in slow patterns. The bright side faces the sun, The dark side is outlined by the faint glow of cities and the soft band of the atmosphere catching scattered light. A little farther out, the planet is no longer a landscape, but a sphere. Oceans and continents blend into patches of blue, brown, and white. Rotation becomes the most obvious movement, a steady turning. One full spin every 24 hours. The noise of local events disappears. What remains is a simple rhythm, like a slow wheel moving under constant illumination. From the distance of the solar system, Earth is one point among several, following its path around the Sun. The star at the center does not show its boiling details. It is a stable disk of light. The orbits can be traced as thin, invisible lines, each with its own period. Over time, the inner planets move like the hands of a clock, each hand turning at its own pace. The drama of eruptions and magnetic storms is hidden inside that regular, geometric motion. Moving farther still, the Sun itself becomes just one of many stars in the galaxy. The spiral structure, the dark lanes of dust, and the scattered clusters of light extend across a vast field. The memory of individual planets fades. Only the overall pattern of the galaxy remains. A slow rotation that takes hundreds of millions of years to complete a single turn. In that view, the solar system is a small detail in a much larger, slowly changing design. Beyond the galaxy, other galaxies appear as faint patches and elongated streaks. Some are similar spirals, others are more irregular. Supernovas, gamma-ray bursts, and all the extreme events that once occupied the center of attention become part of a quiet backdrop. They are short flashes on timescales that are otherwise dominated by very gradual change. Light from distant explosions arrives as a thin signal added to the general glow. At this scale, the universe looks calm. Expansion is not something one can see as motion in real time. It is inferred from the way light is stretched and from the patterns in the oldest radiation. Space seems almost still. The violence that shaped matter into its current forms is spread thinly over an enormous volume and long intervals. The immediate impression, if one could look at it all at once, would be one of wide, soft dimness. From that wide view, we can bring the focus back in slowly, without haste. First, to the galaxy, still turning, then to the solar system, with its planets following their quiet paths. Then to Earth, rotating under a thin atmosphere, night passing into day, day passing into night, at a pace that has not changed much over long periods. The extreme events remain present in the background, but they are distant enough to leave this small orbit mostly undisturbed. As the image settles on the planet, attention can narrow even further, until it returns to a single point on the surface where someone is lying still, breathing at a regular pace, under a sky that might be clear or covered in clouds. Above that sky, the layers continue in the same order: atmosphere, magnetic field, space, the orbit of the moon, the pull of the sun, the larger patterns of the galaxy, and the expansion of the universe beyond. Nothing in that structure is absolutely fixed, and nothing is completely safe from change. Yet, at this moment, all of it holds together well enough to provide a long interval of relative silence. The great explosions are far away. The beams of radiation point elsewhere. The sun shines at a level that bodies and ecosystems on this planet have already adapted to over long periods of time. With that in mind, it is possible to let the details fade a little. The names of objects, the numbers, the processes can step back. What remains is simply a sense of scale and distance, a small world, moving through a wide, mostly quiet space, surrounded by events that are powerful but, for now, not close. In that picture, there is room to rest inside the pause, knowing that the larger story continues, but not needing to follow every line of it tonight. Looking back at the entire picture, The universe did not develop along a certain path, but walked a very narrow line between countless possibilities of failure. It was this fragile balance that created a space quiet enough for complex structures to appear, and vast enough for them to continue evolving for billions of years. Thank you for accompanying us on this slow journey. As the rhythm of breath eases and thoughts settle, we can pause here. But the story is not over. Ahead still lie surprises, secrets, and deeper layers of the vast universe waiting to be discovered. Together, in the silence,